In this last video for the 10,000X high voltage homemade probe, I'd like to go over a schematic for the probe. I also plan on running a voltage breakdown test on it. For your standard 10X probe, you'll have some type of compensation network down inside of the base, and there'll just be a series resistor with some type of parallel capacitance. This would typically be your oscilloscope here. It has some internal capacitance and a 1 meg internal resistance. For the 2 kV homemade probes I made using the shell casings, I have a series resistor in the tip and then a high voltage resistor. This was a 10,000 volt part, and then I had some ferrite driving out to a coax and then back to your oscilloscope. In this case, the capacitors here were 2 pieces of wire that I had painstakingly trimmed to compensate for the coax out here. So there was no other trimming adjustments with this, and I got very good results with these probes. Originally I'd only planned on running these at 2 kV. I had them hooked to a DC supply for an afternoon and never had any problems with them. When I was running my meter tests, I had actually ran them all the way to a 4,000 volt transient and had no problems with them at all. Frequency response on these is quite good, in excess of 100 megahertz. This is what they look like. These are just soldered together shell casings. You can see here the BNCs are soldered at the back. They're just covered in some heat shrink tubing. You can see the brass up here, Teflon, and there's pogo pins in the ends of these. So very simple, cheap. They're only good, like I say, maybe you can run 5 kV. I probably wouldn't run them up higher because it's going to break down eventually internally to the brass case here. My highest voltage probe that I had is this Tektronix P6013. This is a 1000X probe. This probe's good for 12,000 volts using a peak pulse. If you watch my meter testing, I had ran it all the way up to 13,000 volts. It seemed to work fine up there. I felt I was kind of pushing my luck. This is the whole reason I'm building the higher voltage probe, is to exceed the performance of this probe. So if we look at the schematic for this type of probe, again, you have some type of series resistance and a capacitor in parallel with it. And then in the base, there's a cap for the low frequency compensation. There's a resistor down here that sets up the gain of the probe. And then there's these other RC networks that set up the different frequency trims. This is looking at my 10,000X probe. And again, we have these 2 series resistors. These are Super Mach from Ohmite. They are a 940K. This is a 10 watt non-inductive device. They're 1%, 50 ppm parts, and they're rated for 45,000 volts each. Just like my shell case probes, there is a stub, which is a piece of magnet wire that runs along the length of the 2 resistors. And there's a shield, which goes to ground, and that shield encases the stub as well as the 2 resistors. So there's a resistor and a capacitor that are in parallel that tie the stub back to the 2 resistors. So this is your output signal here. There's a gas discharge tube in series with a MOV. These are here in case this 2 resistors were to arc over. This will basically shunt that power back to ground and hopefully save our scope. Because the GDTs are quite slow, you can see I've got another series resistor here. And then there's a very fast transorb. Hopefully this will clamp it fast enough that it'll protect the scope. There's another capacitor out here. This is for very low frequency. There's another set of trim caps down here. One of these is set up for very low frequency. The next set is for a mid-range frequency. And this capacitor here trims the high frequency. You can see down here there's another GDT and a MOV. So if it were to arc from the probe down to the stub or anywhere along the length of this, again, it would basically shunt it directly to the shield ground and back out to our circuit. So that's basically the design in a nutshell. I show these capacitances here going back to the resistors. Again, that's the antenna of the stub, is the high frequency capacitor. This could be drawn. This is essentially your parallel capacitance that would normally be in the tip of the probe. The shield itself will also couple down to this stub, as well as it also couples down to the resistors. These parasitic capacitances also have to be dealt with. The way I've handled that is I've got quite a bit of distance between that ground in the center conductor. You can see here again I'm just using a ceramic tube for this, so as the conductor feeds down the center we have quite a bit of air gap in here. Okay, so for this last bit of testing, what I want to do is some type of a breakdown voltage test. My concern is that can I really get 40,000 volts into this probe and actually not have it break down. I've had the probe attached to a neon sign transformer. Open circuit wise, I got about 20,000 volts out of it. I've also had it attached to my transient generator I used to test my multimeters. However, that transient generator right now will put out about 13,000 volts. It's a fairly high energy hit, but it's not enough to damage this probe. This probe is designed to handle well above what either of those two sources can put out. To come up with a high voltage source that's fairly low energy, I'm choosing to use a car ignition coil. So this is a coil that a friend of mine gave to me. It is for wasted spark, so the output is isolated, so it actually has two wires coming off of the output of it to drive the two spark plugs. So I basically just have an IGBT driver that I built to drive this coil. If we're looking at the output of the coil, you'll see the coil turn on and I'll get some type of a voltage out of it. If we're looking at the current going through the primary coil here, you'll see that current start to rise, and eventually I regulate that, so you'll see the current go flat, and I'll hold that in regulation and eventually just release it. And the edge on that will be quite fast, and you'll see the voltage then rise up. In this case I'm going to be using a spark gap. Once the gas is ionized, it'll draw quite a bit of current and the voltage will drop down, and it'll sustain this ionization until it runs out of energy. Once the coil runs out of energy, it'll ring out and go back to ground. The rise time for this is typically a microsecond or so, and the sustained time out here is in the millisecond range. So we're talking about fairly low frequencies that we're using with this, but again, what I'm interested in is this voltage up here. I'm hoping with the car coil we can test at much higher voltages than what I've been able to test the probe with so far. This is looking at our car coil here. You can see I got a couple high voltage boots, and they're offset because I'm trying to get the distance of these two wires away from each other. Otherwise it'll actually arc across this way. So you can see here I've got the probe just attached directly across the output of the coil. There's a slight air gap between the two pieces of wire. This is the driver over here. This is just a basic IGBT driver. This is currently being triggered off of my ARB. This output here is a current monitor, so I can watch the current through the primary of the coil with this. This will put out 1 volt for 10 amps. These pots here allow me to regulate the current through the coil. You can see on the probe itself I've removed the outside shielding. For these tests what I want to do is look to see if anything breaks down. So this just gives me access to look down inside the tube. So I'm going to go ahead and turn on the power supply. And you can see our little gap here arcing. It's not very large. What we want to do is start out fairly small and then just slowly increase this gap, and then again monitor to see if anything breaks down in the probe head. So the probe is actually hooked to the oscilloscope right now. So the red trace here is the current through the primary of the coil, and this is currently 5 amps per division. So you can see I'm putting out about 8 amps or so. You can see here the current goes up fairly linearly, and once it reaches whatever my current limit is, I just hold it flat, and then I turn off the driver here. Again, if we looked at the voltage here, this would just come up and go down here. So as I'm turning on the voltage, you can see the output from the transformer increases. I get a little bit of ringing here, then it remains flat until it goes into regulation, and we'll see it start to oscillate again. And at this point here we have a very high voltage spike. This area here is where we ionize the gas, and it sustains that again until the coil runs out of energy to drive it. And then you can see here this is the ringing, and this is where the final heat is dissipated inside of the coil. So currently this is 2 milliseconds per division out here. The ionization happens over a period right now of about 4 milliseconds. If we zoom in and we look at the high frequency pulse here, again this is our high voltage. You can see here it rises again fairly linearly and eventually it arcs over. And then you can see the rapid decline before we go into the ionization phase. Right now we're looking at 5,000 volts per division. You can see we're putting out about 10,000, 15,000 volts right now with the gap the way it's set. Okay, so I'm going to slowly start increasing the gap here. It's a fairly large gap now, about 1/4 of an inch or so, maybe 3/8. This is currently 10,000 volts per division here. So you can see we're at about 20,000 volts and everything looks fairly normal. Again, the output looks fairly smooth. This is pretty much what we'd expect to see right now. So yeah, 20,000 volts does not seem to be a problem. Okay, let's just we'll go ahead and increase the gap a little further. And again, I don't see anything inside of the probe. Just visually looking down inside of the end of it here, it looks pretty good. So this is looking at 20,000 volts per division here. So we're now about 40,000 volts. So yeah, the waveform looks pretty good. Part of the problem now is we're putting out enough noise where the USB mouse is starting to flash. I'm seeing this thing already resetting. I don't have the scope located too far away right now. It's probably maybe 5 feet away from the arc, but I've had troubles in the past with USB devices getting reset. They're not very immune to noise like this. Right there, it just it reset. You can see the light just flashed. LaCroix should offer their own mouse that has a some type of EMI rating for it. Quite the arc now. We're probably 3/4 of an inch or better. And again, looking inside of the tube, everything looks pretty good. I'm not seeing any kind of problems there. And right now we are 20,000 volts per division. So you can see we're putting out about 60,000 volts. So this is looking down inside of the tube here. Let's see if we can increase the gap a little bit further. Yep. And there's the breakdown. I don't know if you saw that, but like right between the lip here, right there. The ends of the copper now have been actually coated with Corona dope. In case it arcs and it blows across the edge here. Hopefully here this is going to seal the end of that. So all the dope's drying here. That might be kind of interesting if we took a look at some of the insulators that I'm using. This is the high density plastic that I use. Get that better from the side here. See how far that arc is traveling now to get around that plastic barrier. Stuff works pretty good for high voltage. We're probably clearing about an inch overall now. Same thing with the ceramic tube here. Tough to get a good shot with this. You can see it takes quite a bit to get it to blow through this stuff. Part of the problem with testing this open like this as well, the end of this insulator is made out of Teflon, And this Teflon again inserts down inside of the bore of this ceramic tubing. So I had anticipated this thing arcing somewhere from the center conductor on up here. There's Teflon on the inside here, but eventually that stops once we get near the resistors. So there's an air section in here where we don't have a lot of protection. So the idea is that the Teflon is going to protrude down inside of the tube to add that insulation barrier. So once this all gets assembled, I don't think that any breakdown here is going to be a concern. So here we have the probe assembled. And I can slide the two electrodes apart where it stops arcing. This is about the limit of what I can get out of this coil. It's about 15 amps now a drive, and you can see we're not really gaining anything at all as far as the output. Still roughly about 60,000 volts. So yeah, I'm saying that's pretty much the end of the transformer. It's the same car coil here. It's connected up to an MSD ignition. This is a high performance CDI ignition. And we'll see if we can get a little bit more juice out of that coil. Right at 60,000 volts. It's pretty good. See, the waveform's quite a bit different using this CDI ignition. So the gap now, that's probably about 5/8 of an inch or more. Let's go ahead and turn her on. And we're starting to cause the scope to wig out. You can see here the mouse is completely shut down now. So we're generating a little bit too much noise now for the scope to be able to handle. You know, it's 20,000 volts per division. So this would be 70,000 volts up here. It works pretty good. No signs of anything breaking down or anything. But it looks like, yeah, it looks pretty good. So I think we're going to call that quits for this part of the testing. So my PC, which is located, it's probably 6 feet away or so from the ignition source right now. You can see again the USB mouse is completely disabled. So you power cycle it, come back online. It's a pretty common problem with the USB not being able to withstand a whole lot of noise. Power cycle it, it'll come back. I've had this with numerous USB devices, so not uncommon for me to see this kind of a problem. Looks like 65,000 volts, no problem with this thing. Again, I'm not sure frequency response. Several megahertz anyway, so looks pretty good. I think the last thing I'm going to do here is make the handle for it. And if you did plan to build something like this, you'll notice that my probes don't seem to follow what a lot of people are doing out on the internet as far as interlacing parallel capacitors with a bunch of resistors and chaining them all up, where I'm just using a piece of wire. So it's definitely a little different, but I'd say probably more common to what you would see in a real high voltage probe. The compensation on this thing, again, quite a bit different than what you would see for normal probes, I'm sure. Again, I was trying to get the compensator back in the handle so I could just use some standard coax with this, and it seems to work pretty good, so I'm pretty happy with the results. Anyway, I hope you enjoyed the video. Later.